Okay, this is the 5th video in chapter 15, and we're going to talk about writing net ionic equations first. So what net ionic equations are the equations involved in a chemical reaction that only tell you which species, which ions are actually reacting in a given mixture of compounds. So I'll just start by saying, usually when you're given a formula equation, like a neutralization equation, when you're given the formulas, I'll call this more general, I'll call it a formula equation. What this formula equation is telling you is it's saying you mixed reactant A with reactant B. And when that reaction occurred, here are the products that were produced. Well, as it turns out, for some chemical reactions, especially chemical reactions that are aqueous dissolved in water involving ions, not all of the ions are actually participating in the reaction. Some of them are what we call spectator ions. So how do I know which ions in these formulas that are given, like HCl is a molecular formula, sodium hydroxide is an ionic formula, water is a molecular formula, sodium chloride is an ionic compound formula. How do I know which ions, like sodium or chloride or hydroxide or hydrogen ion, which ones of those are chemically reacting and which ones are not reacting in the mixture? Well, the way that I'm going to figure this out is by using this method to solve for my net ionic equation, what's really going on. The first thing we're going to do is that we're going to write the total ionic equation. Instead of the formula equation where everything is nice and pretty, we're going to really expand this to show every ion that's dissolved in water above. So what you do if you're asked to write an ionic equation is you start with the formula equation you're given. From that equation, show all of the ions are in solution. Basically what this means, if something's in solution, it will have the aqueous symbol beside it. Aqueous means dissolved in water, or it's been ionized in water. So you're going to break the aqueous compound down to show all of the components of the ions. For example, this is kind of what you do when you do a double replacement reaction, when you kind of try to figure out how the cations switch anions. So we'll look at an example here. We have hydrochloric acid plus sodium hydroxide yields water plus sodium chloride. We actually just looked at this neutralization reaction in the last video. Acid plus base equals salt plus water. Alright, so what we're going to do is we notice that the acid and the base and the salts are all aqueous in this equation. So the first thing we're going to do is we're going to ionize or dissociate them. So every time you have an aqueous, you're going to write the cation and the anion separately because in solution they're dissociated from one another, right? Alright, so we're going to write the total ionic equation. So instead of writing hydrogen chloride or HCl, we're going to write the hydrogen ion. Now, remember, hydrogen is in group 1A on the periodic table, so it has a +1 charge. Chlorine is in group 7A, so its ion has a -1 charge. So I'm going to write the charges of the ions. That aqueous meant that it was dissolved in ions. So I'm going to write the hydrogen ion separate from the chloride ion. And I'm going to maintain that they're both aqueous because they're both still dissolved in water. They're just dissociated now. Alright, I'm going to do the same thing with sodium and hydroxide. Sodium's charge is +1, hydroxide is always -1, so I'm going to write those ions because they're aqueous. I'm going to separate those ions. And then we've got hydroxide. And this is going to yield water plus sodium chloride. Now notice that water isn't aqueous, or water doesn't dissolve in itself to form ions. So we're just going to keep water as a liquid. We're only going to dissociate the compounds that are aqueous. So sodium chloride's aqueous, so we're going to dissociate it into sodium cations and chloride anions. So those are both aqueous. I'm running out of room here. Alright, so this is the total ionic equation. We've got all of the aqueous species dissociated. Alright, from here, what we're going to do is we're going to come up with the net ionic equation. The net ionic equation is done by removing something called the spectator ions. Spectator ions are ions that do not change from the reactant side of the reaction to the product side of the reaction. The ions still floating around in solution in both the reactant and product. So they're kind of floating around in the water while the reaction's taking place, while bonds are either being formed or broken. Alright, so I'm going to look on the left-hand and the right-hand side of the equation. I'm going to start with hydrogen here. I have a hydrogen ion on the left-hand side of the equation. Do I have a hydrogen ion on the right-hand side of the equation? No, I don't. I have water, sodium, and chloride. So I don't have a hydrogen on that side of the equation. There we go. So I only have hydrogen ion on one side of the equation. That is not a spectator ion. If it's not a spectator ion, we're going to bring it down. If you're not a spectator ion, if you're not just watching the reaction happen, that means you're actually part of the reaction. You're going to be part of the net ionic equation. You are actually reacting. You were there before and now you're gone, right? Okay. Let's look at chloride. Here's chloride on the left-hand side of the total ionic. Is it on the right-hand side? Yeah, chloride's on both sides of this equation. It has not changed. We call chloride a spectator ion. What we're going to do is we're going to cross it out. It's on the left and it's on the right. So we're going to cancel that out. Spectator ions are not part of the reaction, so they will not be included in our net ionic equation. Okay, let's go to the next one. We have sodium. Sodium ions found on the left hand and the right hand side of the equation again. So sodium is not part of the chemical reaction. Let's go to hydroxide. Hydroxide's on the left hand side of the equation, but we do not see a hydroxide on the right. Hydroxide's not a spectator. It's actually part of the reaction, so we're going to bring hydroxide down because it's part of the actual reaction. It changes. It's on the left-hand side, but it's not on the right-hand side. So it was chemically reacted. And now we have the right-hand side of the equation. Notice that the only thing left is water over here. We have water on the reactant side, but not product side, but not the reactant side. So it's not a spectator. Water is actually part of the reaction. So what were our spectator ions? The sodium ion and the chloride ion were both spectators. They weren't involved in the chemical reaction at all. The chemical reaction was hydrogen ion plus hydroxide yields water. The acid plus the base yielded water. This is usually the net ionic equation that you'll find for most neutralization reactions. It'll be the proton plus hydroxide yields water. So that was literally the chemical reaction taking place, the forming of a chemical bond between these two compounds. Alright, so that's an example of writing a net ionic equation. Let's write another net ionic equation. I hope you like these because actually when I was in Chemistry 1, these were like my favorite things ever. I don't know, I just love doing net ionic equations. I guess because I like to figure out what was actually going on in the equation. So, if someone asks you to write a net ionic equation, what are you going to do? Well, the first thing is, if you're given the formula equation, it's all nice and it's all pretty, everything's there, it's written well, there's no charges anywhere. The first thing you've got to do is you've got to ionize everything. If you see anything that's aqueous, dissolve it, break the ions apart. So the first thing I like to do is I like to find all the things that are aqueous. See all the aqueous things there? And I like to kind of make squiggle marks here. Alright, I'm squiggly marking everything. Because if it's aqueous, that means it's dissolved in water, which means it's not in compound form. The ions, the cations and the anions are literally floating around solution. Let's see here. So let's go with sodium carbonate first. So we said sodium carbonate is going to dissolve in solution. We're going to get sodium cations and carbonate cations. Before you actually do anything to write the equations, let's figure out the charges. Remember that sodium cations are always +1. Carbonates are always -2. Alright, let's go to hydrogen and chlorine. Hydrogen we said was +1. Chloride was always -1. So just go first and mark what your charges of things that you know they are. We're going to deal with subscripts and superscripts and stuff like that later. Not superscripts, coefficients. So here we have sodium chloride. Sodium's +1, chloride's -1. Do we need to just dissociate anything else? No, we don't, because we have a gas and we have a liquid. Gases and liquids are not part of the solution, so they cannot be dissociated. All right, we're going to go back and we're going to write the total ionic equation. And I will try not to make this messy. Because, first of all, have you ever tried to write with a stylus? Oh my gosh, on a little iPad. I'm not good at writing anyway, as far as I'm not the neatest writer ever. This makes it really hard. And now I'm going to try to draw so small so I can fit all this in. So let's try our best here. What are we going to do when we write the net ionic equation? Or the total, I'm sorry. We're going to break all the ions down and show their charges individually. Everything that's aqueous. So here we have sodium. We know that the sodium ion, and I'm going to get really sloppy with my aqueous, that's aqueous there, as a +1 charge. But when this thing dissociates, we talked about this in a previous video. When something dissolves in water and dissociates, do you remember that you can look at the formula to determine how many of each ion dissociate? We know sodium is Na +1. We know carbonate is CO3 -2, aqueous. All right, but how many sodiums do we have? We have 2 sodiums. I'm going to bring that 2 out front. What happens is the 2 sodiums are not bonded to one another anymore. They're floating around independently in solution. So we have 2 sodium atoms floating around. We only have 1 carbonate atom, so that just stays as it is. All right. Let's go to the next one. We have 2 HCl's. Do you see how we have 2 there? That means we're going to have 2 hydrogen ions and 2 chloride ions floating in solution. So the next thing that we're kind of learning as we go here is that if you have a coefficient in front of your compound, you have 2 of each of those ions. So we have 2 hydrogen ions floating around in solution, aqueous, and we have 2 chloride ions floating around in solution, aqueous. All right. Now, arrow. I don't think I'm going to make this fit. I'm going to try my best, though. All right. So over here we have 2 sodium chlorides produced. 2 sodium chlorides produced. That means that we have 2 sodium cations and 2 chloride ions. So 2 sodium cations. That's an aqueous. And we have 2 chloride ions. Aqueous. There we go. And then we have our carbon dioxide, gas. And we also have our water, which is a liquid. I did not have enough room, but I wanted to keep everything on one side or the other, not to confuse things. Okay, so we have our reactants on this side, our products on this side. All right, this is the total ionic equation. Everything's been ionized in the proper quantities. You want to be stoichiometric here, so keep your numbers of each ion correct. And that keeps your formula balanced. I guess I should say if your formula is not balanced in the beginning, you better balance it. But most of the time it is with us. All right, let's go on. After you write the total ionic equation, your next step before you're writing your ionic equation is to get rid of all the spectator ions. For every ion on the left-hand side of the equation, if it exists on the right-hand side of the equation unchanged, it's a spectator. It's not part of the reaction. So we're going to get rid of it. So, for example, we have 2 sodiums on the reactant side, and we have 2 sodiums on the product side. That's a spectator ion. It's not part of the chemical reaction. We have a carbonate on the left-hand side. Do we have a carbonate on the right-hand side? No. So carbonate's part of the chemical reaction. We're going to bring that down. So for our net ionic equation, these are things that change from the left-hand side to the right-hand side. They chemically react. So carbonate chemically reacts because it's not found on the right-hand side of the equation. All right, what about hydrogen ion? The hydrogen ion's on the left, but it's not on the right, so it's going to react as well. So we have carbonate plus 2 hydrogen ions. And then let's see, what else do we have? We have 2 chlorides on the left hand and right hand side of the equation. So those are spectators. We have carbon dioxide only on the right hand side, and we have water only on the right hand side. So those actually are a part of the reaction. Let's see here. How am I going to do this? So we form carbon dioxide and water. I'm going to go ahead and erase this. So everything that's a spectator has been taken away from our total ionic equation, and we're left with what hasn't been taken away, what's not a spectator ion. And we see that our chemical formula is carbonate. Our total ionic equation is carbonate plus 2 protons yields carbon dioxide plus water. Now, one thing you can do when you get to your net ionic equation is you can always make sure that it's balanced. Like I have 1 carbon and 1 carbon, 3 oxygens and 1, 2, that should say 2 there. It's just written horribly. 1, 2, 3 oxygens. 3 oxygens, 3 oxygens. I have 2 hydrogens. I have 2 hydrogens. And then you want to make sure the charge is balanced too. I have a negative 2 and I have 2 plus 1, so I have a total charge of 0. And then I have a total charge of 0. Everything balances here. That's a good way to check your net ionic equation to make sure that you've written it correctly. But the next question to ask yourself is, does my equation make sense? If I had carbonate plus 2 protons, and if I had plus chloride yields carbon dioxide plus water, well, if there's a chloride on one side of the equation and it's not on the other, chances are you made a big mistake, because we can't just lose chloride. It doesn't disappear, right? We have this law of conservation of matter. So as it turns out, usually when you get to your net ionic equation, it should make sense. Okay, so we're going to go back, and we just finished talking about net ionic equations, the reactions that usually happen, that actually happen when you add different formulas of compounds together, the reaction that's actually occurring. And when we talked about neutralization reactions, when you have a strong acid and a water-soluble hydroxide base, we said the acid plus base, strong acid plus strong base, will equal salt plus water. We looked at the neutralization reaction from a net ionic reaction standpoint, and what we ended up finding was that for the acid, what's usually reacting is the hydronium ion. The proton. And the proton reacts with the hydroxide ion of the base. And together they neutralize one another, the acid and base components, to form water. What we see here is that we have a stoichiometric reaction. If we looked at this as molar quantities, for every 1 mole of proton, we need to react that with 1 mole of hydroxide to form 1 mole of water in this chemical reaction. The quantity of acid equals the quantity of base in order to neutralize the solution. In chemistry, we have a procedure known as a titration. And a titration is a procedure that measures the amount of a reagent that's required to react with the mass or volume of another reagent. So we measure how much of one reagent is needed to react with another reagent in order for the chemical reaction to take place. Usually titrations, especially for beginners, are used to determine the amount of acid or base present in a sample. What do I mean by this? Suppose I have a sample of acid, and I know the approximate concentration of the acid, but I do not know the exact molarity of the acid. What I can do is I can put a known volume of the acid into an Erlenmeyer flask. And I want to calculate what the molarity or the concentration of that acid is. Well, I know that acids react with base to form salt plus water. So what I can do is I can add in a certain amount of known concentration base and a known volume of base to my acid. Remember back in chapter 14, we said if we know the concentration of a solution and we know its volume, we can multiply those things together. Molarity times the volume of a substance, do you remember that equals moles? Okay, because molarity is moles per liter. And if our volume is in liters, molarity times volume will equal moles. Okay, so if I know the molarity and volume of the base, I know how many moles, or the quantity of base or hydroxide I put into my acid. The reason why this is important is if you look at the neutralization reaction here at the top, we just said that for every 1 mole of acid, it reacts or requires 1 mole of base to react. So, if I don't know how many moles of acid I have, what I can do is I can measure the moles of base that was required to neutralize the acid, and I'll tell you how we do that in a second. But if I know the molarity and the volume of base used to neutralize my acid, I know the moles of the base. And if I know the moles of the base I use to neutralize my acid, for every 1 mole of base, I have 1 mole of acid. I know the number of moles of acid. Okay? And if I know the volume, then if I get moles divided by volume, I'll get molarity. So what I can do here is I can calculate the quantity, how many moles of acid I have in a certain volume of solution, to calculate the molarity, the unknown molarity of the acid that I want to find. And I do this by a process called titration. Now, how does titration work? Titration, you have your Erlenmeyer flask, and the Erlenmeyer flask contains your unknown concentration. Molarity of whatever you have. But you have a known volume. You're going to use that volume and calculate the moles, and you're going to get the molarity back out. So you have your Erlenmeyer flask with your unknown concentration of acid or base in it. If there's acid in your flask, you're going to titrate with base. And you titrate using something called a burette. A burette is kind of like a pipette. It's really tall, and it's got something at the end of it called a stopcock. And stopcocks are just little basically sticks that stick into the pipette, and they have a little hole in them, and you can turn them to open the flask up to flowing, or if you turn them again, you can stop the flask from flowing, or the pipette from flowing. So you can put a solution in here, and when you put a solution in the burette, this is called a burette, the burette delivers your known molarity and volume, because you can measure, of your base. So if you have an unknown acid concentration, then you're going to put your base in here. The reason this is that you know the volume is that you're going to start by putting a certain quantity of base in. So if you start at 0.0 milliliters, and by the way, the burettes read from the top to the bottom, because you're going to drop your solution into the unknown acid and you're going to react. Every drop of base is going to react with the acid, and as those react, every drop is going to create a little bit of water that comes out. So it's going to neutralize it. Alright, so you're going to start with a certain concentration, a certain volume of your base at the top. You're going to read from the meniscus, and as you go down, you're going to get you're going to read backwards. So the numbers are going to get higher as you go down the burette. 1 milliliters, 2 milliliters, 3 milliliters, all the way down to usually like 25 or 50. So as this level of the base goes down, as you begin dropping, you read how much was delivered. This is called the solution inside of your burette. Your known solution is called your titrant. It's what you're titrating with into the unknown, into the Erlenmeyer flask. Inside the Erlenmeyer flask, by the way, you're going to put something in here. And it's going to look invisible at first most of the time. If you're in an acid solution, you're going to put an indicator. An indicator is a chemical compound that changes colors as you change pH of solution. Usually the one that's used the most is an indicator called phenolphthalein. So phenolphthalein is going in acid solution. Phenolphthalein is colorless. But when you're in basic solution, so acidic solutions, like if you put phenolphthalein into your unknown acid, it will be colorless. As soon as the solution becomes basic, meaning there's any excess hydroxide, even 1 drop excess hydroxide after the endpoint is when the acid and base are neutralized. So if you add any excess base after that, it will turn a pink solution color. So this is phenolphthalein. It's an indicator that's usually used for acid-base neutralizations. It's the most common one. Alright, so you're going to deliver a certain volume, a known volume, and you have the known concentration of the base in here. You can calculate the moles of your base, that's your titrant that's used. If you know your moles of titrants, once this thing turns pink, you know your moles of acid. From your moles of acid, if you know the volume, moles divided by volume gives you molarity. So you can actually calculate the molarity of your acid. Let's go ahead and look at some examples of how we can, and actually we'll just learn by example what a titration problem looks like and how we can use the known titrant molarity volumes, the unknown molarity but the known volume to calculate the concentration of the unknown in our Erlenmeyer flask. So here's this first problem. It says if 22.59 milliliters of 0.1096 molar HCl, let's just stop there. Here we're given a volume of HCl in milliliters. So we know the volume of HCl, and we're also given the molarity of HCl. So we know the molarity and volume of HCl that's used to titrate. So this is our titrant. So this is our known compound that we're going to put inside of our burette. Is used to titrate 25 milliliters of sodium hydroxide. So the sodium hydroxide solution is the unknown. So here we have HCl, and we know the molarity, and we know the volume that was used to titrate. It started at 0 probably, and you went down to 22.59 milliliters as you went down, as that dropped in. And here we have sodium hydroxide. The sodium hydroxide, we know that we have a volume of 25 milliliters of this stuff in the Erlenmeyer flask. And it's got phenolphthalein in it as our indicator. And it says, what's the molarity of the sodium hydroxide? So we know the volume in the Erlenmeyer, but we have no clue what the concentration is. The titration method is used to calculate that. So here we're given a chemical reaction first. I'm going to erase a little bit of this. So we've got HCl as our known quantity of our titrants. We know the molarity and the volume, and we want to know the molarity of the sodium hydroxide, but we only know the volume so far, but we know the molarity and volume of HCl that was used to turn the phenolphthalein to its endpoint. Now the phenolphthalein always inside of this flask. It's our indicator. The phenolphthalein is in base, so it starts out pink and then it's going to turn colorless whenever one excess drop of hydrochloric acid is added. So let's look at the chemical reaction. It says HCl plus sodium hydroxide equals water plus NaCl. We know that really what's going on here, we've got one hydrogen in HCl, we've got one hydroxide in sodium hydroxide, so one hydrogen plus one hydroxide yields one water. This was our net ionic equation that we got from our neutralization reaction earlier. So if you want to go find out how to get this equation, go back and watch doing net ionic equations. But this is really what's going on. So what I know here is that for every 1 mole of hydrogen ion, it requires 1 mole of hydroxide to neutralize it to the end point. This is whenever all of the hydrogen ion or hydroxide ions quench each other. They chemically react to form water. We become completely neutral. So basically, I can change this to X and X. For every X moles of hydrogen ion, I know that I have X moles of hydroxide ion in my solution. So how many moles of hydrogen ion did I add? Well, the moles of hydrogen ion in our acid is going to be the molarity of the acid times the volume of the acid. So the moles of the acid, I'm going to change that to acid and base. The moles of our acid is going to equal the molarity times the volume. So let's see here. I've got to do this on my calculator. The volume right now is in milliliters, so I'm going to divide the volume by 1,000 so I can get moles out. So the molarity, it said, was 96 molar. That's moles per liter. I'm going to change molarity to moles per liter so that I can cancel out my units. And the volume right now is in milliliters, so I'm going to divide by 1,000, so that'll be 0.02259 liters. I'm so bad, but I'm running out of room. So at least you're listening and you know what I'm doing, right? All right. So I've got 0.1096 times 0.02259. And the liters cancels out the liters. We get our moles of our acid that's consumed in this chemical reaction, our titrant. And I get 0.00248. I'm just going to round it. Moles of our acid. So the moles of acid that's used is 0.00248 moles. Remember that the moles of acid that are used or consumed by the volume of titrant added equals the moles of a sodium hydroxide consumed in the reaction as well. So the moles of acid equals the moles of base. So I'm going to come over here. I've got 0.00248 moles of our sodium hydroxide. Now we want to know molarity. Molarity is moles divided by liters of solution. We know from the problem that we had 25 milliliters of sodium hydroxide. So 25 milliliters, let's divide that by 1,000 again to get it in liters, because molarity is moles per liter, is 0.0250 liters, right? 25 milliliters divided by 1,000, 1, 2, 3 is 0.0250 liters. Okay, so I'm going to divide these numbers. 0.00248 divided by 0.0250. I get the molarity of my acid, or my base, I'm sorry, as being 0.0992 molar NaOH. So that's how we solved the problem. Let's break down how we solved it again, alright? We solved it because we knew the neutralization reaction said that the moles of the hydrogen ion that reacted equaled the moles of the hydroxide ion. We knew we could calculate the moles of the acid because we were given the molarity of the acid and we were given the volume of the acid. Molarity times volume equals moles. So once we were given the molarity and volume of the acid, we calculated the moles of the acid. We converted this to moles of our base. And then to get the molarity out, moles divided by volume in liters equals molarity. So we finally solved for molarity by converting what we were given for the acid to moles. We did a mole to mole conversion, and then we finally just calculated molarity, moles divided by volume. So this is like a very, very, very big problem. If you can solve this, you are doing good, because it involves skills from chapters 14, concentration, solutions, and chapter 15. So that's an acid-base reaction using titration. So practice, practice, practice. There's more in your book. I could use all the time in the world, but practice the problems in your book. Start with all the example problems. On page 353, there's 3 example problems. They walk you through how to solve these, and they give you strategies. And then, of course, there's always more example problems in the book that you can try. So practice is going to make perfect on this chapter, okay?